Okay, this lecture is going to focus on impulse, which is defined as changing momentum. Instead of a quote, what we have a picture of the Starship Enterprise because what it's described as is described as the impulse engine. Now, the impulse engine would be something that would be changing the momentum of the, in this case, spaceship, but really any engine is going to be doing that. Anything that allows you to change the velocity is going to change an object's impulse. So you should understand the factors that determine impulse, and you should be able to relate impulse to change in motion and change in momentum. You should also understand the key things in terms of impulse and momentum in designing safety equipment and in playing sports. So the first thing is this. Impulse, depending on what book you're talking about, is defined as J or delta rho. Okay, so either J or delta P, both of those mean impulse. Impulse is defined as change in momentum. So the reason why an object will change momentum is there's going to be a force exerted on it. So if you have a mass that's moving at a certain velocity, in order to change the velocity, you must exert a force on it. So this is what we're talking about Newton's second law. Newton's second law was originally written in these terms because this right here, this change in momentum has mass and change in velocity. This has force and change in time. Well, you can rearrange these things and you can take velocity and change in time and you can get acceleration out of that. So really, the impulse momentum equation is nothing more than a restatement of Newton's second law. It's actually the original statement. Now, impulse can technically be either Newton's time second or kilogram meters per second. Now, impulse, to distinguish it from momentum units are kilogram meters per second. So the impulse units are generally referred to as Newton's seconds. And the reason for that is they just want to make sure that they're keeping the two straight. So car safety. A lot of car safety devices use this idea of impulse momentum to increase passenger safety. Now, when you look at the equation that we just talked about, there's really a couple of factors. So mass, change in velocity, okay, and then force and time. The ultimate goal of any safety device is to reduce the force that is exerted on the passenger or whatever's in there. So really, if I want to take this number and I want to make it very, very, very low, I can either make this side low, or I can take this time value and I can increase that time value. Well, whenever you have a car or something like that, you can't really change the mass of the car. You can change the velocity of a car by using the brakes or traveling at a slower speed, but for a lot of times that's not really realistic. You can't go on the highway and go 10 miles an hour in order to be more safe because it ends up producing other problems. So really, what we're looking at in terms of safety equipment is we want to be able to reduce this time right here. Now this time is very specifically called the impact time. So if we can increase that impact time, it has a result of decreasing the force. So what we do is we take a look at dashboards, materials that cars are made out of, the design called a crumple zone, seat belts, airbags. All of these things that are done right here are designed to increase the impact time. Okay, a dashboard was originally metal. Okay, metal is not flexible at all, nor is it soft. Okay, so the reason why metal would hurt if you were to hit your head on the dashboard is this time factor would be very, very, very small. If you have a small time factor, you have a large force value. Okay, same thing with the different materials. Cars are no longer really made out of steel anymore. Most of them are made out of synthetic plastics. Same thing. It increases the impact time. Crumple zones. Okay, the car's designed so that it will actually fold into itself to increase the impact time. Okay, all of these increase the impact time, thereby reducing the force that's exerted. Okay, this question says, what functions do airbags have as they relate to change in momentum? Remember, when we're talking about change in momentum or impulse, we have delta P equals F delta T, or mvf minus mvi. So, the airbag cannot change the velocity of the car. It cannot change the mass of the car. But what it can do is that it can actually increase the impact time. So the time that it takes for the collision to occur. If this number is a set constant value, which it is in a particular car crash, you want to increase the time as much as possible to decrease the force. Okay, this question says, why should you roll with a punch? So that's a kind of a famous expression that says roll with the punches. So the reason why you want to do that is a couple of things. If you look at the impulse momentum equation, remember your goal is to reduce the force. That's what we're trying to do. By moving backwards or rolling with the punch, you are actually increasing the impact time, the time that the glove is in contact with the face. But what you're also doing is you're actually changing the final velocity of the glove. Okay, if a glove comes and hits a face, usually the fist comes to a stop. But that creates a greater change in momentum on this side. But if this is originally, say, 10 meters per second comes to a stop, if you roll with it and move backwards, now it's moving at maybe 1 or 2 meters per second. It greatly reduces this. So not only are you reducing this side, but you're also increasing the contact time, and that has a dramatic impact in reducing the force. Okay, this question says determine the force, so we're looking for F. If the impact lasts 0.75 seconds and brings a 2,000 kilogram car from 60 miles per hour to a stop. So I'm going to go ahead and just underline that because you should know by now that miles per hour is not something that we deal with, and you should be able to recognize that's something we're going to have to convert. So we're going to be we're trying to relate force, okay, to time, to impact, and all those things. So we're going to say Ft equals mvf minus mvi. Now, I don't know for sure that that's the formula that I'm going to use, but it's the one that makes sense with the most variables that I have, and it does allow me to calculate force. So basically what we have is we have a car that's crashing into, say, a wall, and the force is going to be exerted in this direction to bring the car to a stop. So you have an initial velocity, and then it says it brings the car to a stop, so our final velocity is going to be 0. Because you're changing the velocity to the left, the force has to be to the left as well. And a lot of people say, what do you mean I'm changing the velocity to the left? The velocity comes to a stop. Yes, but it's becoming more and more left. If it was right to begin with, increasing to the left actually causes it to come to a stop. So we say, what information do we have? We have the time is 0.5 seconds. We have that the mass of the car is 2,000 kilograms. We have that it comes to a stop, so we know the final velocity is 0. And we know that the initial velocity is 60 miles per hour, which to convert, you should know by now that converting miles per hour, you multiply by 1,600, divide by 3,600, and you get 26.7 meters per second. All right, so now we've identified our given. We can plug everything in. We can say, all right, Ft equals mvf minus mvi. Or divide both sides by t, and basically what you have is F equals ma. Because this right here represents A now, with the mass, of course, being out there. But this is the form that I want it to be in, so I would say F equals 2,000 times 0 minus 2,000 times, okay, now in this case you can't forget the negative 26.7, excuse me, I already did the negative, 26.7 over t. So now we plug in our numbers into the calculator. We say 2,000 times 0 is 0. So what I have is negative 2,000 times 26.7 divided by 0.75. And you get an answer that's negative 71,200 newtons. And people usually have an issue with that. They say, well, how can I get a negative force? That doesn't make any sense. Remember, look at our original diagram. We said that I was moving in a positive 60 miles per hour here. The force is in the opposing direction. So the fact that I got a negative just tells me that I'm moving in the opposite direction. Now, if the question were to ask,
what is the magnitude of the force, you would of course answer this as positive 71,200 because magnitude is an absolute value of whatever vector value you're given. Okay, this is a graph question. We haven't done graphs in a while. It says determine the impulse in 10 seconds. Now remember, impulse is another word for change in momentum. So what I'm trying to solve for is delta P, which I can get by saying F times T. Now you should remember by now that whenever you're trying to do F times T, when you're multiplying two things on a graph together, we're finding the area. So basically what I'm trying to do is I'm trying to find the area under this graph during the first 10 seconds. Now, I actually divided this graph up for you so it's easier for you to be able to figure out, number one, that you should be finding the area, number two, how to do it. So what I do is I have a triangle right here to begin with. To find the area of a triangle, remember triangle is 1/2 base times height. So what I have is 1/2 the base would be 2, so 1/2 of that is 1. 1 times 10 would be 10. Okay, I have to do the same thing here. I've got a triangle. 1/2 of 1 is half. Okay, and then a lot of people want to say that the height is 20. It's not. Remember, the triangle is drawn is 10. So this actually has an area of 5. And people will make that mistake because they'll say it looks exactly like that triangle. Remember, you have to look at the scales. Okay, you also have a triangle here that has a base of 3, and this one does have a height of 20. So 1/2 of 3 times 20 gives you an area of 30. Now I can look at the rectangles and squares. Rectangles and squares are just base times height. So 2 times 10 is 20. 1 times 10 is 10. And 2 times 20 is 40. So now in order to find the overall impulse, I just have to add these terms together. So 20 plus 10 plus 10 plus 40 plus 30 gives us a value of 110 plus that 5, you get 115 Newton meters. Okay, this question is also a graph question. It says determine the change in velocity of a car with a mass of 5 kilograms at 4 seconds. So remember, when we're looking at the change in velocity, that's defined as delta V. Now I can actually get delta V using the impulse if I were to look at my equation. My equation is Ft equals mvf minus mvi. But if I were to take and factor out that m, what it really is m times Vf minus Vi, which is, by definition, delta V. So you have m delta V is equal to Ft. Well, it tells me the mass of the car, which is 5 kilograms, and it tells me, or gives me this graph of information that was force times time. So if I could find the area, which is the impulse, the Ft, that would be the other side of this equation. So we actually already did this in the previous example. We know that this is 2 times 10 is 20, and we know that this right here was 10, 1/2 base times height. Now if you look, it says at 4 seconds, so we actually cut it off right there. So now we have 30 on one side, we have 5 delta V on the other, divide both sides by 5, you get delta V is equal to 6 meters per second. So as a result of this acceleration for this, or this force for this amount of time, the car will actually change its velocity by 6 meters per second. Okay, this question says, what is the impact time, or the T, that results from a 10,000 Newton force accelerating a 100 kilogram object from rest to 40 meters per second. So you have some sort of 100 kilogram object, and we're going to apply a force of 10,000 newtons to it, which is quite a bit of force, and that's going to take it from 0 to 40 meters per second, so almost 100 miles per hour. And we want to know how long the force is in contact with this object. So we know we're going to use Ft equals m Vf minus Vi. So if you look, our given information, we are given the force is 10,000. We are given the mass as 100. We are given the initial velocity of 0, and we are given the final velocity of 40. What that allows us to do is we can now say 10,000 t equals 100, 40 minus 0. 40 minus 0 is 0, so this ends up being 4,000. So you have 10,000 t equals 4,000. Divide both sides by 10,000, and you get t is equal to 0.4 seconds. Okay, this says a cannon is set on a frictionless surface. So you have a cannon that's set on a frictionless surface. Whenever you have this cannon, it's going to shoot, it says it shoots 12 shots per second for 3 seconds. So we know there's 36 total shots. So if we know there's 36 total shots, and it says that a 1 kilogram projectile is initially motionless, so we have the mass is given as 1 kilogram. And we have the fact that it is initially motionless, or VI is 0. And then it says it's fired at 100 meters per second. So the final velocity ends up being 100 meters per second. So now we know that this whole thing occurs over 3 seconds. So if we look at this, we have our information that we can say Ft equals mvf minus mvi. And what we're trying to solve for is the force. Now we're trying to solve for the force that's exerted on each of the cannon shots. And when we do that, we can then say, hey, equal and opposite forces say if you're doing this for one, you got to do it for the other. So we're going to go ahead and just plug in this 36 in for the mass, and it's going to simplify our problems. Because if you're shooting 36 1 kilogram shots, that's the exact same thing as shooting one 36 kilogram shot. So we say that F, and then we're going to say T, and our T is 3 seconds, is equal to M, which is 36, times VF minus VI. So we have F is equal to 3,600 over 3, or the force that's exerted is 1,200 newtons. Now, if I were being a stickler in terms of direction, the direction of the cannon would actually be negative, because what you're solving for when you get this positive number is the force that's exerted on the cannon shots. This is the final and most difficult of the examples on impulse momentum. It says a 0.4 kilogram super ball is dropped from a height of 25 meters and rebounds to a height of 20 meters. If a force of 28 newtons is responsible, so we have the force that's exerted as 28 newtons, what is the contact time? So we are trying to solve for the time. Now, since we're talking about force and time and all that, we know we're going to use Ft equals mvf minus mvi. However, I do not actually have the times. There's going to be 2 times that are going to be involved in here. The first one, or excuse me, 2 velocities that are involved here, and I got to figure out what they are. So the first one is the initial velocity in the collision. So the initial velocity in the collision is when the ball is moving downwards just as it strikes the surface. And then I'm going to have the final velocity, and that's going to be the velocity as it moves upward after rebounding. So we're going to have to be real careful here when we're starting to look at this. How am I going to figure out those velocities? And what I'm going to do is I'm going to use conservation of energy, or MGH equals 1/2 mv squared. Okay, in our case, mass is going to cancel out for this calculation that we're doing. So we're going to say that the fact that it falls 25 meters times 9.8 allows me to solve for the velocity that it's moving as it strikes the ground. So 25 times 9.8. Move the 2 over to the other side. Take the square root, and you get the velocity as it strikes the ground is 22.1 meters per second. Now, this is what I found by doing potential energy being changed to kinetic. But this has to be negative. The reason why it has to be negative is actually moving down as it strikes the surface. Now what I'm going to do is I'm going to solve for this final velocity using the exact same method but in reverse. I have a potential energy that's 20 times 9.8 equals 1/2 velocity squared. What that allows me to do is I can say 20 times 9.8, take the square root, and you get a velocity of 19. We'll call it 8 meters per second. Now that is a positive velocity because it's moving upward. Now that I have these two velocities, I can now plug in my original question and solve for the force. So it tells me that I have a 28 Newton force. I'm trying to solve for the impact time. I know that the mass of the Super Bowl is 0.4. I know that my my final velocity is 19.8, and I know that my initial velocity was a negative 22.1. So if you look, 19.8, which is my final, minus a negative. Remember, when you subtract a negative, it becomes plus a positive. So what you have here is you have T is going to be equal to 0.4 times 19.8 plus 22.1, which is 41.9, and then all of that is over 28. Divided both sides by 28 there. So 0.4 times 41.9 divided by 28 gives 0.599 seconds, which is an awful long time with what actually happens with the Super Bowl.
So by now you should understand the factors that determine impulse. Remember, impulse can be determined by comparing two momentums and subtracting, multiplying mass by the change in velocity as opposed to just velocity, or by taking the force and multiplying it by the time. So using those factors to determine impulse will then allow you to turn around and relate it to motion. So you have an effect on the velocity somehow. You should understand the importance of designing safety equipment and in sports. Remember, whenever you want to hit something really hard, you follow through because it actually increases the impact time on the bat. Whenever you follow short, the force is exerted over a small time, so there's not as much a change in momentum. Safety equipment works a little bit differently. You want to increase that impact time, thereby decreasing the force.